So it's my pleasure to welcome today's speaker for today. We have with us Dr. Thibault. He did his master's degree in sports science at the University of Nantes in France and his PhD in cognitive neuroscience at the University of Lyon. And he is currently working as a postdoc in my lab. And today he'll be telling us about some of the work he's been doing studying tool use deficits after left hemisphere shift.
Right, thank you for the introduction. So yeah, I'm gonna present some more that we're currently doing at MOS under this version of Dr. Aaron Wong and also Dr. Royal Bugsbone. So I will talk about tool use deficit after left hemisphere stroke. So let me I'm not sure. The next slide. All right. So today's prior family visiting study is supported by a generous gift from Nancy and Marc Shrier. We are grateful for their support and belief in our mission. Here is the code that you may need for those that are having the CME credits, but if you don't have, so I will give you some time to take the note of it, but if you don't have time, no worries, I will show the slide again at the end of the presentation. So I don't have any financial relationship to disclose for this presentation. And okay, let's start with what I'm going to talk about. So my presentation for today will be in two different sections. The first section, I'm going to talk about tool use deficit in hemisphere. And so I will present some data, preliminary data that's been collected on that. And second section will be more about naturalistic action deficit in hemisphere. So by that, we'll talk about like more daily life situation, and not only like single tool use. It will be the case in the first section. Yeah, I think it's gonna be of interest because yeah, in daily life situation we are especially patients, we have to interact with different tools. So I won't have any data to present on that, but I will talk about the project that I'm planning to do. All right, so tool use deficit in hemisphere. First thing that might be worth doing is defining what is the hemisphere. So it's a puzzling neurological condition or disorder that will affect movement, and especially what might be considered as complex movement, such as imitation, pantomime. That is when we are asking participants or patient to mimic how to use a tool, but without the tool in their hands. So if, for instance, I'm doing that, we probably say that I'm using a comb. Or also they will have difficulty to use real objects. So like with us, they may have like single tool use deficit, or they may have naturalistic action deficit. So those two last one will be the main interest of this presentation. And that's important to mention that those deficits are observable with both arms. And that cannot be, those deficits cannot be attributed to any elemental motor or sensory motor deficits, such as the hemiparesis that are usually observed in the right arm. And yeah, so we can also observe those deficits when we are testing the non-paretic arm, that is usually the left arm. And let me illustrate some of those deficits with one of our patients that we ask here to use a toothbrush. And as you can see, she's not performing like the usual movement that should be this type of movement. And she was also using the tool at the level of the neck and not really at the level of the mouth. Same patient, here with a pair of scissors, you will see that even though she's gonna correctly, not correctly, she's gonna succeed to cut the piece of paper, the way that she's grasping the tool is not conventional at all. So yeah, she had quickly to configure the hand with respect of the Thibault. And another thing that I'd like to define before talking a little bit about neuroanatomy is, I mean, what is tool use? Because when I'm saying people like friends, family, or colleagues that I'm working with tool use, they always ask, what is a tool? And I think this definition, actually, that it's coming from people working on animal tool use, actually fits pretty much with what might be considered as a tool. So a tool is use of an object to alter the form, position, or condition of another object, another organisms, or the user itself when the user holds or carries the tool. So that might be then a lot of objects, and that's what I've represented here with lots of objects that probably you are using in on a daily life basis. That might be then considered as tools. And regarding like limb apraxia and the tool use deficits, that can be observed in a lot of, or not a lot of, but some different condition, neurological conditions such as Parkinson or Alzheimer's disease, the autism spectrum disorder or cortical basal degeneration. But actually, in our lab, we are focusing on limb apraxia that is observable after left hemisphere stroke or cerebral vascular accident. Yeah, just the two pictures of one patient with a left stroke, and in comparison, a brain of neurotypical person, where you can see that there is like this huge lesion in the left hemisphere stroke and a lot of area of the brain that are affected. And actually, when we are talking about left stroke, not all the patients are approximate. There's not a very precise estimation with precise proportion, but yeah, so far studies suggest that they may have like 30 to 60% of left stroke patients that may show some sign of apraxia. I guess it depends how we define apraxia and the test that you are performing. So this, yeah, so I was showing like some example of tool use deficits in apraxia patients. And I told you that it's those patients have like a left hemisphere stroke that's the patient that we're interested in. So that's raised question about what is the contribution of the brain and what if there is like a tool use network in the brain. And to talk a little bit about that, I will talk about the studies of Brandy and colleagues. That is kind of interesting because, to the best of my knowledge, it's the first one that's where they ask participants to use tools in a fMRI scanner. That is kind of a challenge because you are constrained by the space and you need to avoid like big head movements in this type of experiment. But yeah, in this study, they were asking neurotypical participants to use tools, and they were comparing like the neural activity for those tools versus a bar that you can see here. That is not a functional tool. They were just moving the bar into the target wheel. And when they did that, they compared them, so tool use versus the bar neural activity, and they were looking at two different phases. The one that is the planning phase and the execution phase. So for planning, there were no movement. They were just preparing to do the tool action. And what you can see is that even though there were no movement, there is still already like some activities that are specific to the tools. And those activities for planning were more like in posterior part of the brain, still in the left and mostly in the left hemisphere. with involvement of the parietal area and also like occipital temporal part of the brain. I will go back a little bit later on some of those regions. Then when they had to execute or use the tool, there was still like more activation in the left hemisphere, still a lot of posterior activations, with maybe more and bigger involvement of the intraparietal sulcus that you can see here, and also maybe more anterior portion of the occipitotemporal junction with the middle temporal areas. But also what you can see is that in addition to those posterior parts of the brain, there were involvement of the more anterior part of the brain with the premotor cortex. There is like the result of meta-analysis, where basically they find some relevant hub for tool use, and the more the color is red, it means that there were more studies finding involvement of this part of the brain for tool use. And let me go through some of those critical hub in tool use and explain what might be their contribution in the tool use process. So the first one that I'm going to talk about is the posterior middle temporal gyrus. That is associated to tool use action, tool action knowledge, and also they have like in this part of the brain they are like overlapping and tool representation, and that might also explain why this part of the brain might process tool action knowledge. Then there is the inferior parietal lobule that is a critical hub, one of the most critical hubs for tool use, that is doing a lot of different type of computations, and some of them that have been suggested and found so far that this part of the brain might be involved in the memory of skill gesture and postures associated to tools and tool use, action prediction, and also like more recently mechanical problem solving. So for instance, if you have to use a tool that you are maybe not that much familiar with, you may have to reason about the way that you will have to use this tool, and that might be one of the functions the IPL is doing. And then there is the superior parietal lobule that is not totally specific to tool use, but that is found to be involved in tool use for the reason that I will explain right after. So basically what this part of the brain is doing, it's aggregating different sensory inputs, such as proprioceptive and visual inputs, to build like a common body representation, and that will support at the end grasping and reaching movement. So that's not tool use specific, because you can grasp and reach objects, such as a cube, for instance, that is not a tool, that doesn't have like a specific function. But yeah, so the SPL will be involved for this type of action, but when you are also grasping and reaching, grasping a tool, that is found to be part of the tool uniform. And then more anterior part of the brain we are talking about, and likely more involved for the execution parts, might play a role in motor command preparations. And I forgot to mention, the name of that is likely the premotor cortex. All right, so it's possible that the beginning of my introduction gives you the feeling or sensation that those patients have like tool use deficit with any type of tool. And actually that's not true. If we look at in the past literature, we can notice that those patients doesn't have any grasping, the deficit, they might be able to grasp any object correctly, or if we are considering tools such as a stick, they might be, so this one, they might be able to point correctly in different location in the space with the stick. Whereas if we consider tools such as the bottle opener, they may have more difficulty. And then that's not really clear what makes tool difficult to use for practice. So again, to illustrate that, if we consider like one of our patients using a fork. That might be considered a little bit like a simple stick. She's doing quite well. There is no observable deficit in this example. But no, same patient with a better opener, she has much more difficulty. She's first turning around the tool. She has struggled to perform like the lever movement that you should do to open the bottle. And the end position is not very good as well, probably too close of the tooltip. And at the end, she's gonna miss to open she's gonna face, sorry, to open the bottle. So why are we observing this difference in the same patients? One of our hypotheses that tool use might be difficult for apraxic because motion of the arm and motion of the hand is different than motion of the tooltip. So let me clarify that. We were interested by two parameters that were aiming to test this hypothesis. The first one is when the tooltip and hand movement are incongruent. So I was talking about the bottle opener. When you're using a bottle opener, you need to do like the lever movement, and basically your hand will need to go down, whereas the tooltip will go up. So there is like a mismatch within the two motion. Or another good example is like the closest spin, where basically you have to close your finger to open the tip of the closed spin. That's how we define incongruence. Then second parameter that we were interested in is when the tooltip and its handle are laterally displaced. So two real life examples to illustrate that, the manual egg beater, where you can see that the handle is not aligned. There is like a lateral displacement with respect of the tooltip. And another example is to illustrate that is the fishing game. Okay, so we were interested to test those two parameters, and we performed like first experiments. So far, we included like 23 participants, among them 14 FCVA patients, and we tested their apraxia severity and also controls. Did this? So we were testing, sorry, the apraxia severity with a test for apraxia, a battery of tests for apraxia, sorry, and controls were also doing this battery of tests, and that allowed us to estimate a cutoff define the patient as apraxic or non-apraxic. We obtained also lesion map for a subset of the sample. Here what you can see is like the lesion overlap map where more red part of the brain means that there were more patients with lesion in this part of the brain. And we asked those participants and patients to use a tool to move a puck into a square using the left hand, so the hand that the non-paretic arm for patients, and they were performing like 6 repetitions with each tool. So we are manipulating different parameters to build our set of tools. And the first one was like we made like unconstrained stick. And so let me clarify the task first. So that to move to use the tool to move the puck here and to move this puck into the square that you can see. And we have like a not displaced version of the stick, and then the laterally displaced version of the stick. And then we have tools that were constrained by a pivot. This one is considered as congruent because, like in the example that you will see here, the motion of the hand and motion of the tooltip have the same trajectory. So both are going forward. And then we have like incongruent tool, incongruent because, as you will see here, like motion of the hand and motion of the tooltip are going in 2 different directions, with a backward movement for the hand and forward movement for the tooltip. And yeah, we have also like the laterally displaced version for the congruent and incongruent tools. So we are recording kinematics, and we are interested by two different phases. And before talking about these phases, let me explain what we are seeing here. Here you have like velocities in blue for the hand, that is the left hand. In red for the tool handle, and so right here, sorry, and in green for the puck motion. And basically we look at a phase for initiation or planning that was defined by the reach to grass phase, where they may have like some, even though the hand is already moving, there are some online adjustments or planning processes that are involved in this phase, and just before like they start using the tool. And then there is the use phase that is defined from the first movement of the tool handle until the puck is inserted. And if we look at data collapse across tool, we first found that there is initiation impairment for apraxics, where you can see that's the reach to grass time. There is like a longer time for apraxic in comparison to control, but also like non-apraxic stroke patients. There is also a use impairment, so we are quantifying that by the tool peak velocity. That is like an index of vigor, that's how much vigor that the participants are putting in the use phase. And we can see that this tool peak velocity was much smaller for apraxic in comparison to controls, and we got like a numerical difference versus non-apraxics. And yeah, so we found like both initiation and use impairment. And as I told you, also we ask our participants to perform like 6 trial with each tools, and so that is possible. There is like some learning effect, and so we were interested to consider and look at what is the time course of the behavioral performance. And so for that, again, we collapsed data across tool, and we look at it across the 6 trials they were performing, and we found that there were a learning effect. But as you can see, apraxic were on the initiation were much slower in comparison to the 2 other group. They get a little bit better, but we're still like impaired at the end of the task. And we found a similar pattern on the use part with impairment early on in the task, some improvement, but still impairment later on. And so, because we found this relation, we were interested to look at the effect of apraxia severity in relation to lateral displacement and congruence in the early phases of this experiment, when like apraxic were apraxic were more impaired, and also before like the learning process totally took place. So that's what we did here. So this slide might be one of the most difficult to understand. So try to be like very focused on this topic. So we first look at the effect of apraxia severity on the initiation phase with respect to the lateral displacement. And we found an interaction between apraxia and lateral displacement. And here it's like the apraxia severity score. So those participants on this side of the axis are more apraxic patient, and then here's less apraxic patient. And here what you can observe is that more apraxic patients are slower to initiate movement towards laterally displaced tools. And the relation was not as steep for non-displaced tool here in blue. So yeah, for the displaced tool is this one, and non-displaced the blue one. Then we look at whether this relation could also be found on the use phase, but we didn't find any interaction. That is that apraxia severity has the same effect on both displaced and non-displaced tools.
But they're actually faster, more more apraxic people are, oh, no, that's velocity, not RPE.
Yeah, that's
Sorry.
velocity.
Sorry, okay.
Yeah, I forgot to mention that. Yeah, they have like a smaller.
All right.
All right, and then we look at the effect of approximity with respect to congruence on the initiation phase again. And we didn't find any interaction again. That is, regardless of approximity, they were behaving the same way with congruent and incongruent rule. But then when we consider the use phase, we found an interaction that is more apraxic patients have more difficulty to use congruent tool, whereas it's not the case for less apraxic patients. So that's basically the red line that you can see here. So how to explain that? We think that the interaction we are observing for lateral displacement is found during the initiation because that's something you can perceive from that's something evident, let's say, something that you can perceive easily from the initiation before interacting with the tool. Whereas for congruence, that's especially for patients, maybe more difficult to figure out if it's a congruent or incongruent tool. They may need to interact and to have the tool in hand to figure out if it's a congruent or incongruent tool. And so we also did like some very preliminary lesion subtraction analysis. So I've presented during the introduction that we use is involving a network that is mostly left lateralized and involving more frontal parietal part of the brain, in addition to also occipital temporal part of the brains. And we did this lesion subtraction analysis. So we use like our dependent variables. One for initiation, that is the reach growth time, and we split our sample between fast and slow patients, and we subtract the lesion between those two subgroups. And basically what we found here is like more posterior parts of the brain are involved for initiations, with the superior parietal lobule that you can see here, right there, and also like the posterior middle temporal gyrus. And then for the use phase, we did also the same, and we again found like involvement of posterior part of the brain with superior parietal lobule right here. And in addition to that, involvement of more anterior ones with the ventral premotor cortex right here. And that's, even though that's very preliminary analysis on a tiny sample, that's kind of interesting to observe those results because it's pretty consistent with what I was presenting early on in the presentation. That is, more posterior regions are involved for planning, whereas in addition to more posterior region, there is also an involvement of more anterior one for execution. Okay, let me conclude some of the main points on this first experiment. We found like tool-related impairment in apraxia, that tool-related impairment in apraxia impact both initiation and use. That apraxia exaggerate initiation impairment for laterally displaced tools and use impairment for congruent tools. And that initiation impairments might be explained by more posterior lesions, whereas use impairment will be additionally associated with more anterior ones. Yeah. Next step would be to test our assumption on actual tools, and so I have actually some data to present about that, not directly with actual tools, but more about pantomiming action with actual tools. So I will explain that right now. So what we did in this second experiment. So we were first asking neurotypical participants to rate how much a tool, all the tool that you can see on this slide, were incongruent. We are asking them basically, we did that through an online survey, and we asked that question: how much do the hand movement to use this tool differ from the motion of the functional part of the tool? And so that's the result that we got. So here you have like the median across all the items. And you can see that a tool such as a carjack or the clothespin were considered as much more incongruent. Whereas a tool such as an iron or a comb were more considered as more congruent than incongruent. And actually, for a large subset of those tools that I was presenting, we ask our patient in our approximatory LCBA patient to pantomime the use of those tools, to mimic basically how they will use this tool. And so we are scoring some errors like end posture error, arm posture error, and amplitude timing error. So let me give you an example about that. So if we are considering like the comb, if like let's say the end posture like this, probably not a very conventional way to pantomime. It's like if I'm on the arm posture, if I'm putting my arm here, that's probably not also a conventional way. I'm not sure it's like errors that patients are doing, but it's just to illustrate. And then amplitude timing is like if I'm doing this movement, for instance, is not very conventional as well. And then timing is like more the speed of the movement. So if I'm doing this movement, that's probably not coming as well. So that's the type of error that we are coding and scoring for each of the tools. And so here, what you can see, so you have like the amplitude timing pantomime accuracy and the median here. And you can see that for tools such as the carjack and clothespin, they are not very accurate to pantomime that. Whereas for the comb and iron, so far on the 15 HCA patients that we had, they didn't do any pantomime errors only for the amplitude timing part. And we did like we compute like a correlation between amplitude timing pantomime accuracy and the incongruence rating, and we found like a significant correlation, negative correlation here, that suggests that the more a tool is incongruent, the more patient might do errors. And so here you have like some of the example that I was talking about before. Or yeah, the more they're gonna do error, to say it differently, the less they will be accurate with incongruent tools. But yeah, if we are thinking about the carjack, maybe you will say, yeah, but I'm not using like a carjack every day, which unless you are very unlucky, but so we are wondering if there might be like some confounding factors in this effect that we are observing. And so actually in the online survey, we were also like measuring different parameters such as tool familiarity. So that's the question we're asking for familiarity, but we're also asking like mechanical reasoning. How already talked a little bit about that in the intro, but how difficult it is to figure out how to use a tool. And also like the use graph conflict, that is a parameter that's been studied for a long time, especially by Laurel in the lab. And that is how grasp and use and movement differ. And just to clarify that, if you think about like a beer mug, when you grasp the beer mug and then when you use it, basically your end posture will not change. But if you think like about a keyboard, so not on the laptop, but like a separate keyboard, this one, for instance, right here. When I'm gonna grasp it, I'm gonna grasp it like this. But when I'm gonna use it, I will do this movement. So there is like this conflict between use and grasp. And so we did like this matrix of correlations. And so when we consider only amplitude timing pantomime accuracy, we found that only incongruence correlates with this accuracy. If we consider like the average of the different errors, such as end posture, arm posture, and amplitude timing error, we found that incongruence correlates with total pantomime accuracy, but also that use graph conflict correct with that. That then suggests for this one that tools that are more conflicting on the use graph side are also more difficult to pantomime. And that's consistent with a lot of evidences that have been published so far by our lab again. So let me conclude about that. So the more a tool is rated as incongruent, the more LCVA patients will perform amplitude timing errors when pantomiming. Also, like the total pantomime accuracy correlates with both incongruence and graph use conflict ratings. And neither familiarity or mechanical reasoning correlate with pantomime accuracy. And then, again, next steps. Anyway, will be to test how much apraxia severity affect the use of actual incongruent tools, and not only looking at pantomiming. But yeah, that's a follow-up goal, but I don't have data right now to present on that. Now let me just need to check the time. It should be okay. Let me talk about naturalistic action deficit in linear apraxia. Why I'm going to talk about that. So in the first part, I was mostly talking about single tool use deficits, but actually in real life context, we are not rarely using one single tool. We have to pick up different tools and perform like a sequence of actions by interacting with different objects. Especially if you think about preparing a meal, you will have to use a lot of different tools and objects. So there have been like some studies that were interested by that. Yeah, sorry for the reference. I just noticed it's not the right year. It's 2004, I think. But anyway, so in these studies, they ask left brain damage or left stroke patient to perform like naturalistic action or task that is making a cup of coffee and fixing a video recorder. And they found like that left brain damage patients were much more impaired in comparison to control, especially to this type of task. And also what was interesting is that those deficits were correlating with pantomime accuracy on a separate battery of tests. And usually pantomime accuracy is one of the proxy or one of the measure that is most important measure that is used to define apraxia. And this relation actually has been found also in two different papers. So that's, I think, important to mention that. This type of naturalistic action experiments have been done also in the lab, where at most it has been this test, naturalistic action test, has been developed by Niana Schwartz and Laurel Buckbaum. And basically what they were testing in this task is different naturalistic actions, such as, again, making a cup of coffee, preparing a toast of bread with butter and jam, packing or wrapping a gift, preparing a ladder, or preparing a sandwich, and also and packing a school bag. So different tasks, and like in the study, there were like different errors, type of errors that were quantified. And here what you can see is, so there is like control group, there is closed head injury, so I think it's called more like traumatic brain injury, and also like right stroke patient and left stroke patient. And why is interesting to notice that in terms of proportion of error, like LCVA patient tends to do more what is considered as sequence errors. And that's then raise a question that we try to reply in this study that I'm planning to do. This question is whether there is like a core action deficit for apraxic that could cause naturalistic action deficits. And that is first not clear how elementary is the sequencing breakdown for patients. And there is like this study from Dover and colleague where they asked participants to perform like a finger tapping sequence, where basically they didn't find any sequencing error. They found also like the learning process. They were learning approximation in black, but they were like also slower. So it's not really clear why those patients are slower on this type of task, if it's like linked to any sequencing deficit. So basically what we are planning to do here is to use this type of paradigm that is called the serial reaction time task, ask them to perform like a finger tapping task. And we are planning to do like this task more naturalistic. So first we have like we are asked them to do like a sequence of different static and posture. So we show them a tool and they will have to make the posture associated with each of those tools. And then maybe one more degree into the naturalistic continuum, we will show them, we'll ask them to make a sequence with actual objects, and we show them a picture of a recipient object on the screen, and they will have to pick up one of the objects and perform the action associated with the recipient object. And in addition to that, we will use the task that's called the virtual kitchen challenge that has been developed by Tania Giovannitti that we are planning to collaborate with. And so basically this task is a virtual reality task testing naturalistic action deficit, and we kind of find a measure of those deficits. And we are planning to look at the link between the SRT task, serial reaction time task, with those virtual kitchen challenge. And some of our hypotheses about that is we expect to find a correlation of with the virtual kitchen challenge performance. Some different condition, or at least, no, sorry, I studied the wrong way to present this slide, but yeah, if patients have like a core sequencing deficit, we may expect to find like a correlation between finger tapping SRT task performance with the virtual kitchen challenge performance. Whereas if it's when they have to sequence more naturalistic events such as and postures, we may find in that case, we may expect in that case to find like a correlation with the static and posture SRT task with the virtual kitchen challenge. And if their deficit is even more like linked to sequencing events that are then even more naturalistic and that involve tools, then we should only find a correlation with the tool use SRT task. All right, so yeah, that's just like what we are planning to do. So I don't have any data to present on that. I hope I will have soon. But yeah, let me then conclude about that presentation. So I first talk about tool use deficit in hemiapraxia. I think the main information to remember is that apraxic have more difficulty to initiate movement towards displaced tool and more difficulty to use congruent tools. And among a set of real tools, incongruent ones are usually more difficult to pantomime for less tool patients. And this first part was more about single tool use, but we think that's very important that we also consider like more daily life or naturalistic situations where participants have to interact with different tools and objects. And that's the plan of the that was the thing that I was discussing in this second part of the presentation. And I think there is a need to investigate whether naturalistic action deficit might be explained by a sequencing deficit. I'd like to thank my advisors, so Aaron Wong, Roy Buxbaum, also my colleague Ren Williamson that did a lot of coding, especially on the approximatory data. The institution and funding agency that are supporting this work, and also thank you for your attention. And yeah, I'm done.
On one of your conclusion slides, did you say that apraxics have more trouble with congruent objects?
Yeah, that's what we found. Like, so if I go back here. So yeah, that's here. So that's what you can see here in this experiment. Like we found like this interaction between approximativity and congruence, and basically there were like no difference for incongruent tools between more apraxic and less apraxic, whereas more apraxic have like more difficulty to use congruent one, like the peak velocity is smaller. And that's what I was saying. We think that this effect might be explained, especially for those patients, that it might be more difficult to figure out if a tool is congruent or incongruent without acting on the tool. They need to act on the tool to figure out if it's a congruent or incongruent. They may have more hesitation regardless of the tool, basically. Whereas maybe less apraxic patients have less hesitation for that.
So then it seems like they'd just be worse across. Yeah,
I don't think it's quite the way you said that they're more impaired for congruent tools. You really need to qualify that, which is that relative to the controls, that it is on the congruent tools that you see the biggest difference between the apraxics and the controls.
So the controls,
controls
have
have
a fair amount of difficulty
with
with
the incongruent, and so do the apraxics. But the apraxic, right, so you have to kind of finish the sentence, not just that the apraxics are impaired with congruent, it's that the difference between the two groups is big. It's an interaction here that you have to, so you just word that a little bit differently.
Okay.
Yeah, the way I kind of think about it is incongruent tools are challenging for everybody.
Yeah.
And then in addition to that, the apraxics also have problems with congruent tools, whereas when you're neurotypical, you don't have that challenge.
It's still, I mean, it still seems counterintuitive in that one of those would seem to require less calculations, period. So if you're not very good at calculations, wouldn't you be better at the simple one than the hard one? But yeah.
Yeah, but I think it's also because it's difficult to figure out which one, the simple one, the other one, like especially only from the initiation phase.
Yeah.
What do you tell them when you show them these? The first of all, I really like that whole tool thing, board thing, which is pretty controlled. I like that. And I think so. What do you tell them with this?
Sorry, can you
If
repeat
you
that?
give this to me, I would be like, what is this? What do you tell me?
So we have like, so I'm not showing those two directly without any instruction. So we have like a practice with tools that are close to this one. Actually, no, we have like a practice where they're not using tools. We just ask them to move the puck with their hand into the square. Then we have like I call it like the very simple stick, where basically it's very close to this one. I just remove like the body of the tool, the handle, and the tip of the tool. And they have to do like some trial with that, and then we are starting the main experiment, where I didn't want to bias my participants, so I just tell them your goal will be to move the puck into the square, exactly as you did during the familiarization. And with different tools that I cannot show you right now, you will discover it during the experiment, and you will have to figure out as far as you can, and the best as you can to how to use those tools in order to move the puck. So yeah, that's
Getting back to the congruent, incongruent issue, you know, the other tension is between experiment 1 and 2, where the rating study and the correlation of the ratings with the pantomime, their incongruence was indeed a predictor of
Yeah.
pantomime performance. So that's a bit of a different effect than across the.
yeah,
two
but I was
experiments.
thinking about that when I was doing like a very last rehearsal this morning, and I would think that's might be something that maybe link a little bit to familiarity with, even though I didn't find any correlation with that, but like here we are testing other tools and they never interact with the tool. Whereas when you see like an iron or a cone versus a carjack or a clothespin, you may have like some idea about about how those tools have to be used. So yeah, that was the first thing that I was thinking about. Also, the second thing is that we are in the correlation thing. We are considering all LCD patients and not only apraxic patients.
Yeah, so, but fleshing out the first idea a little more, are you saying that incongruence may operate differently with respect to stored tool representations than it does for quote mechanical problem solving, and the
Yeah,
effects might go, you know, and that might be a complication.
that's
Yeah,
yeah. From what I was saying, that may be one of the
Yeah.
interpretations.
I found that an interesting thing about this, and I wondered whether, like, I think you tried to separate a little bit the analysis of the tool from the experience with the learning trials, but I found myself wondering, what if you did this as a virtual tool where you see your hand moves and you see the effect of the tool, but you can't see how the tool itself is constructed. In other words, how much is it analyzing the mechanical properties of the tool, and how as much is it discovering what it does through experience?
Mhm.
Yeah.
And we can look at the learning curve. We do have learning data from within this experiment
that's
to
what I
look
did
at,
too,
yeah,
We
yeah.
also have another experiment we're running in parallel to this that is asking specifically about mechanical reasoning.
Mm.
And so we're gonna look and see how much that relates to this performance.
Did I answer your other question?
And I think there's a question in the chat as well. No, I just had a simple question. What they really liked it. Great presentation. I like this particular manipulandum as well. So why were they wearing the headgear in this study?
Yeah, so again, the same thing. I'm very stressed about my participant to be biased by any visual information. So yeah, I didn't want them to, because I'm changing the tool every trial basically. And so I don't want them to trying to think about how they may have to use the tool. So they have like an 8-second period, and from the go signal, the mask is becoming clear, and then from that point you have to figure out how to use the tool.
To control stimulus presentation is the
Yeah.
short answer.
Yeah. The longest pass.
Yeah, 2 questions.
Yeah, some people just put their email address. So that's I'm not sure why.
Oh.
They're just sign in.
Okay.
So did you control for which hand they use versus what was their dominant hand?
So we are asking, so they all participants have used to with the left hand and they were all right and or because they were patient. Some of them are using, I guess, right now their left hand in real life situation because of the hemiparesis in the right arm. But yeah, they were like right-handed before the stroke.
So do you think that plays an effort on, an effect on how they use the tool? Because if you think of tools like scissors, specifically right-handed or left-handed, and it's very awkward to use with the other hand.
Yeah, that's a good question.
So that would be true for controls as well.
Yeah.
Controls have difficulty, but the difference between controls and LCD
Yeah.
is essentially what accounts for
That's right.
Yeah.
Yeah.
But I was thinking, especially because I think you're making reference to the example that I was presenting with the scissor, right? Maybe.
Yeah, I think so, yeah.
Yeah, I had also this feeling that I was wondering that it could be like the left hand, but yeah, I think Sarish is right. If you think about controls, we didn't observe such deficit. So, and also maybe less apraxia. That's also why we are doing this apraxia severity to have like information about their apraxia severity, and even like stroke patients won't have this type of behavior.
Just thinking, I'm not sure if this would add complexity to it, but what happens if so you have a tool that's common and that's incongruous with the action that you're doing, which is complex. And sometimes in daily life, we use a tool that we know does something, but we use it for something else, like a pair of scissors to hit the nail in or something.
Drive a screw or something.
And so I don't know whether that's interesting or not, but it's just a thought that I had that presumably that would just add to reaction time or something.
If we are asking them to use like a tool with a non-conventional way, is that what you mean? Actually, there are some study about that. Ozuraic stuff that is linked to mechanical reasoning stuff as well. That's all the theory of this guy. That is, when you are using tool, you are not even storing a memory about how you have to use the tool, but it's all about mechanical reasoning. And they say that especially with this study where, if I'm not wrong, they asked only, it was a single case study, but they asked an apraxic to do single tool use, and they didn't have any impairment to do like single tool use with the conventional way. But as soon as they ask more tasks that they were considering as more mechanical reasoning stuff, such as using a knife to drive a screw, this specific patient has a deficit, and they say, oh, okay, they have also lesion in the IPL, blah blah blah. So IPL is doing only mechanical reasoning, but that's maybe.
Yeah, there's a
shortcut.
big literature on divergent thinking and creative problem solving with tools. And that what's interesting is that it tends to, these are a lot of fMRI studies, they tend to invoke the IFG, inferior frontal gyrus, for this kind of out of the box creative thinking, as opposed to the parietal lobe per se. So whether this single case really is a good reflection on whether it's the apraxia syndrome that would cause such a problem, or a broader problem in thinking creatively that really hasn't been explored.
No, yeah, I think it's interesting to read, but I feel like there are a lot of questions that needs to be answered before saying it's only mechanical.
Yeah.
We should probably wrap up.
Yeah.
Thank you.
Thank you.
Thank you.